Okay, so let's move to chapter 10, rational function. So what is a rational function? So let's review polynomial function. Okay, so we say polynomial function is a generalization of integers. Like 312, we just can write this as 3 times 10 squared plus 1 times 10 plus 2, right? So if the base change to x, so 3, 1, 2 based on x, so this number is 3x squared plus 1x plus 2. Or just, so that's just 3x squared plus x plus 2. Right? So this is polynomial function. So we say polynomial function is just a generalization for integers. So for integer over integer, so the p over q, we call such number a rational number. So then for polynomial over polynomial, so such a function we call so the function as a rational function. So rational function is just a polynomial or polynomial, right? Okay, so for rational number, like 2 over 3 and 11 over 3, so we those are rational number. So we separate those rational number into two parts. We say, first one is a proper rational number, and the second one is improper. So how can we separate the proper and improper? So for first one is we find the numerator is less than denominator. Right? For second one is numerator 11 is larger than denominator. Okay. So for improper rational number, like 11 over 3, we can separate this as 11 over 3 can be written as 3 plus 2 over 3. And we sometimes we put them together as 3 and 2 over 3, right? So for rational functions, we also have proper rational function and improper, improper rational function, proper, improper. So how can we separate them? So we say like this function is a proper rational function, and this one is improper. So you can see how can we separate proper with improper, right? So we call this a improper because degree in numerator is less than degree in denominator. And so for this is improper rational function because the degree in numerator is larger than the degree in denominator. So we just check the degree in numerator and in denominator. Okay. So like here we have three rational functions. The first one is pop, and the third one is impop. So how about the middle one? X minus 1 over x plus 2. So for this rational function, we find the degree in numerator and the degree in denominator are equal, the same. So for this one, so we can should we set this as proper or improper? So actually, it is up to us. So we find for our convenience, we just put this as a prop. So we just split this into, so we call those a prop and those are improper. So we can say improper meanings the degree in numerator is larger than the degree in denominator. So for improper rational number, we can do separation, right? Like 11 over 3, we can put this as 3, the integer part, 3 plus a proper rational number. So for rational function, improper rational functions, we also can do that. So how can we find, so how can we separate? So let's just check this, like how can we separate 11 over 3 as 3 plus 2 over 3? So we just find those numbers, we just regard this as divisions. 11 divided by 3. So we find quotient is 3 and the remainder is 2, right? So actually this number, this part is quotient and this is remainder. Okay, so for rational function, we just do the same way. We just regard this as a division, and this part is quotient, that part is remainder. So let's check the quotient. So let's find this division, find the quotient, and the remainder. So here, x squared 0x negative 1. So divided by negative 2, right? Okay. So first one bring down, saying this time this plus this negative 2, and for negative 1, 3, right? Okay, so we know this is a quotient and this here is remainder. So this means we can put this part as x minus 2, and here we can put 3, right? Okay. So for this integer part, the polynomial part, we have a name. So we call this part the polynomial part as asymptote. So we say this function has asymptote is x minus 2. So what asymptote means? So this asymptote is a notation in mathematics. So this means the main part. So let's check this. Like 1000 divided by 3, we find this equals 3, 3, 3, and plus 1 over 3. So we say like this. So compare with 3, 3, 3, there's 1, 3, we can forget this. So we say like 1000 divided by 3, roughly is just equal 3, 3, 3, right? Just like $1,000 separated, can be separated by 3 people. Each one can get $333. So this is some 30 cents. Nobody care, right? So this main part. So this part, integer part, this part, we call this part as asymptote. Okay. So for rational function px over qx, we have denominator. So basic requirement for denominator is denominator cannot be 0, right? This qx cannot be 0. So if qx equals 0, then we call this as asymptote. Because when denominator close to 0, then this rational number become quite big. So this also main part, right? So we call this a vertical asymptote. So why we call this vertical asymptote? Because this solution just x equals some number, like x equal x0. So this x equal x0 in rectangle coordinate means like such a line, right? Like x equal 1, x equal 2, x equal 3. So those are vertical line. So x equal x0. This is the vertical line. So we call this a vertical asymptote. Okay. So now for a rational function, at first we need to find those asymptotes. So for those asymptote, at the first we check the denominator. So denominator cannot be 0, right? So if denominator equals 0, then we say this is the vertical asymptote. Okay. So by the way, so the denominator cannot be 0. We say x minus 1 cannot be 0, so x cannot be equal 1. This is the basic requirement for this function. So we call this requirement as a domain. So domain is cannot be 0. So vertical asymptote is can be 0, equal 0, right? Okay, so then for this function, we find this is improper rational function. So the quotient part is asymptote, right? So how can we find the quotient part? So we just regard this as a division. Okay, so this is 1, -1, -2. So this divided by 1. So first one pulling down, then this becomes 0 and -2. Okay, so this part, quotient part, is asymptote, right? So this 1, 0 means this function y equal x. So we call this asymptote as a slant asymptote. Because the graph for this function is just a slant line, not a vertical line, right? The slant line. Okay. So for this function find asymptote, but again, like at first we need to check the vertical asymptote is x equal 1, right? So the other asymptote is a quotient part. If we regard this is a division, so quotient part is let's say 1 -2 divided by 1. So first one pulling down 1 1 -1, right? So this is the quotient part. So quotient part is y equal 1. So we call this as a horizontal asymptote. HA, horizontal asymptote. So why we call this as a horizontal asymptote? Because the y equal 1, this line is horizontal line, right? So y equal 1, so here's y-axis, right? So y equal 1 is this line, right? Okay. So here if we find for those proper rational function, we have a horizontal asymptote. So how can we determine this horizontal asymptote? Actually, we can determine them quickly. We don't need to use synthetic division. We just check, just check the leading term or just check x over x. So just x over x, just 1, right? So we just check the highest degree terms, or we call those terms are the leading term. Okay, so now let's check this example. Okay, so at first let's check denominator, right? Denominator, we have vertical asymptote. Denominator is x squared minus 1 equals 0. Okay, so we find that we have two solutions, right? X equal 1, x equal -1. So this means we have two vertical asymptotes. Okay, and so this is a proper rational function. So we have HA, horizontal asymptote. So we can quickly determine this HA We just check also. So we have x square, x square. We just compare x square over x square. So just like 2x square over 1x square, right? So 2x square over 1x square, just 2. So we have a horizontal asymptote y equal 2. Okay, so then we consider the graph for rational function. So at first, let's check the simplest rational function, which is y f(x) equal 1 over x. So for scheduled graph, of scheduled graph for a function, we can use traditional way. Old way is just we pick many points and then connect those points. So here we just use the same way, like we use traditional way. Okay, we pick x equal 1 or okay y equal 1, x equal 2, y equal half. X equal 3, y equal 1 over 3, right? So x equal half, y equal 2. Like so we just pick some points. And then also here x can be negative or the negative 1, y equal negative 1, x equal negative 2, y equals us, right? Okay. So then we connect those points, we get the first graph. So this is traditional way. We pick many points. But let's check. We also can use our new ways by asymptotes. So for this function, let's say we have the function thus, right? So at first we just determine its asymptotes. So we have denominator. So denominator vertical asymptote is a denominator equals 0, so x equals 0, right? And this function is a proper rational function. So we have HA. So the HA is y equal. So denominator we have x. Numerator no x. We can regard 0x plus 1. So we can regard the numerator as just 0x. So and the denominator is 1x. So this horizontal asymptote, we just check x over x. So just 0 over 1. 0 over 1 is 0, right? Okay, so we have those two asymptotes. Is x equals 0, y equals 0. So x equals 0, y equals 0 is those x-axis and y-axis, right? So x equals 0 is just the y-axis. Y equals 0 is the x-axis. Okay. Okay. So it's a graph. So graph is just the approach to those asymptotes. So let's pick some points. Let's say x equal 1, y equal 1, so there's a point, right? There's a point. Okay, so then here approach to those asymptotes, go down approach. And here also just approach. Okay, and here we have the point and negative 1, negative 1. So here go approach this asymptote. And here there's the approach to this asymptote. So we get the same graph. But this way is simple. We say so for rational function to schedule the graph, we should use those asymptotes, not pick many points. Okay, so the basic idea is just its graph will approach to those asymptotes. Okay, so let's check some other examples. So for this function, 2x plus 1 or x minus 1. At the first, if we want to schedule graph, at the first we find those asymptotes. Okay, so vertical asymptote is x equal 1, and so horizontal asymptote is y equal 2, right? Just 2x over x. Okay, so the graph is just an approach to those asymptotes. So like here, we at the first we draw this two asymptotes. So the graph is just approach to those asymptotes. So here, let's just say, suppose we have those asymptotes. So approach to those asymptotes can be like this way, approach, or approach, right? So we can pick some points to determine which way. Okay, like here, approach. So we determine A or B. So how can we determine A or B? We can, the simple way is we just pick a point. Let's say like pick a point here. So check a function values here or here. So positive, negative. So we can use this method. Let's say we cannot pick x equal 1, but we can pick x as a little bit larger than 1. Right? Okay, a little bit larger than 1. So from here we can say let's like x equal 1.1. Let's check here if x equal 1.1, x equal 1.1. So there's a function value. So we find is positive, right? So the function is positive. So the graph should be red one, not the blue one. Okay, so for the left side, so this is the one we cannot pick x as 1, but we can, so we just pick close to 1. Let's say, how about x? We just check up there's a point x equal 0.9. So we just check this function if there's a function at this point is positive or negative. So there's a function, I remember this is just 2x plus 1, x minus 1, right? So when x equal 0.9, we find that the denominator is negative. So numerator 2x plus 1 is positive. So the function value is negative, right? Okay, so we know there's a function when x is here, function value is negative here. So we know the graph should be this part. Should be this way. Okay? Okay. So the graph just approach to those asymptotes. Then what we need is just to check which way. Right? Close the, let's say. So we can have many those functions. There's examples, but this idea is quite the same. So here for this function, at the first we find those asymptotes. So at the first vertical asymptote, so x squared minus 1 equals 0. We have two vertical asymptotes, right? X equal 1, x equal negative 1. So we have those two vertical asymptotes. And we have horizontal asymptote, so which is y equals 0. Right? Just the x squared over x squared, right? Y equals 0. So once we have those asymptotes, so then we can sketch the graph. Like let's say that here we have those asymptotes, okay, and here we have this asymptote. So then there's a light part here. Oh, we find just the approach this way, right? So we can pick a point. Let's say so here x equal 1. We just pick a point x equal 2. So we find this y is positive. So we know this graph like that. Okay. So here x equal negative 1. So here just so when we pick x equal negative 2, we find the function y is negative. So the graph should be like negative at this point. So that's like okay approach. So here approach, right? So between these two vertical asymptotes, so we just take, okay, when x equal -1, but a little bit larger than -1, we find if there's a function positive. So we know this approach this approach. And when x equal, let's say, a little bit less than 1, like 0.9, we find the function value is negative. So we know the graph should like approach to down approach, right? Saying between them is somehow connected there. Okay, so we get it as a graph. Okay, so for this function, is improper. So here, proper, improper doesn't matter. Just we just need to determine those asymptotes. So at the first, we have vertical asymptote is x equal 1. So for other asymptote, so this one we cannot compare a leading term. We cannot compare x squared over x, right? We have to use this like things that we use division. So x1 x squared -1 -2 divided by 1. First one putting down 0 -2. Okay, so this quotient part is asymptote. Says y equal x, right? So we call this as a slant asymptote or just other asymptote. We just say other asymptote. So we have those two asymptotes. So we just draw this asymptote. So here, this one is x equal 1, and this is y equal x. So like here we have, okay, this is x equal 1, and this is y equal x. So once we have those asymptotes, so the graph is just, okay, from here approach, or if the point here, then approach, right? We have only two cases, two options. So what we need is just pick when x here is x equal 1, so we just pick a point x like x a little bit larger than 1, so the point is here, function value is here or here. We only needed to determine this. So let's check this. Let's say we just pick this point x equal 1.1. It just a little bit larger than 1. So we find this function value. So just plug in. Okay. So there's a function x minus 1. Put x. No, x minus 1. So this is positive, right? So when x equal 1.1, 1.1 minus 1 positive. So for x squared minus x minus 2, we find this part is negative. 1.1 squared minus 1.1 minus 2 is negative. So we know the function value is negative, right? Okay, so we know the graph should be this part. This, not this. So we know the graph like this. So here the approach, here just the approach. Okay, so for the left side of x equal 1, so here again, like we have this asymptote and this asymptote, so we have only two cases, right? If the point here or here, so if the point here, then the graph is like that: approach, approach, or like approach or approach, right? So we just need to determine which one. So here again, so we just pick a point. Let's say a point less than 1, so 0.9. So we find when x equal 0.9, there's a function value will be positive, right? X minus 1, is negative, and numerator negative, denominator negative, so the function value is positive. Okay, so we know the graph should be this one, right? Should be this one. Okay, not this one, right? So this is the way for schedule graph for rational function. We just need to determine approach those asymptotes from which way to approach them. So let's check this example. This is an example from the textbook. So at first, we say we have a vertical asymptote is x squared equals 0. Or we solve this equation, we say we have only one solution. X squared equals 0, x equals 0. Right? Okay. So then the other asymptote is we just need to regard this as a division and find the quotient part. So this division we cannot use synthetic division because synthetic division is only divided by the first degree polynomial, not the second degree. So for second degree, so we need to use long division. So, but for this example, for long division is quite more complicated, right? But for this example, this division is easy. We just x squared, x3 over x squared equal x, right? And then we can split easily, right? Okay, so this polynomial part is just the asymptote, right? So other asymptote. Okay, so we have those two asymptotes. Y equal x, this line, and y equal x, so this y-axis, right? So, okay, so just approach to them. So let's say we just pick a point here. Let's say here when x equal 1. So when x equal 1, y equal, I think y equal 1 plus a little bit larger than 1 here, right? There's a point here. Okay, so we know the graph is approach. I'm sorry. So here should be the approach like this way. Approach this asymptote, approach this asymptote. Okay, so here just like that, like approach this asymptote, and here this direction, approach this asymptote. Okay. Okay, so those are topic for rational function. So we say for rational function, the main issue is asymptotes. Then once we have those asymptotes, then it's a graph just like approach to those asymptotes. So what is asymptote? So we can regard those as the main part. Just the approach to we just consider the main part. The approach to the main part. Right? Okay. So let's do some problem as the homework. So those homework, I just pick some problem from page 521. So problem 1819 is find asymptotes, and problem 31, 34 is schedule graph. So for schedule graph, so we need find those asymptotes first, right? And 49, 50 is review for polynomial division. Okay. Okay, so we can stop here. Okay, thank you.